Come on, my dears. Today we will finish the whole exercise. First of all, kindly read this statement of first MCQ. Have you read it? Look, they are talking about an intrinsic semiconductor. Remember what is called an intrinsic semiconductor? A semiconductor without any impurity is called an intrinsic semiconductor. Fine. For intrinsic semiconductor, remember whatever is the number of holes in the valence band, same is the number of free electrons in the conduction band. Okay. So I mean to say hole number density in the valence band and free electron number density in the conduction band, both of them are equal. Come on, that's why I am writing here free electron number density is Ne and hole number density is Nh, both of them are equal. But remember, this thing is true only for intrinsic semiconductor. If you are talking about extrinsic semiconductor, that is added with impurity, the doped semiconductors. For that, extrinsic semiconductors are of two types, N-type semiconductor or P-type semiconductor. For N-type semiconductor, Ne is greater than Nh, and for P-type semiconductor, Nh is greater than Ne. Remembered? But this thing is true for extrinsic semiconductor. Right now they are talking about intrinsic semiconductor, for which Ne equals to Nh. Got it? Fine. Now kindly read the statement of number 2. Read it? Come on. At absolute zero temperature, that is at 0 Kelvin or minus 273 degrees centigrade temperature, what happens? Come on. In the pure semiconductor, come on, in the valence band, it is completely occupied. So valence band is completely filled and the conduction band is lying completely empty. Okay, fine. So that's what I have written here. Conduction band is lying completely empty at 0 Kelvin temperature, that is called absolute zero temperature, and valence band is completely filled. Okay. Come on, read number 3 now. Read it? Come on. They are talking about comparison between 3 values of band gap energy. One is for metals, that is good conductors, one is for semiconductors, and one is for insulators or poor conductors. Come on. For metals or for good conductors, band gap energy is minimum, and for insulators or poor conductors, band gap energy is maximum. And for semiconductors, that value is lying intermediate, okay, moderate, in between. Now that's why here I am writing Eg1 less than Eg2 less than Eg3. Band gap energy for good conductors is minimum, greater than that is the band gap energy for semiconductors, greater than that is the band gap energy for insulators. Okay, simply don't mug up this answer. In the examination they may change the symbol. Okay, so accordingly you think. In short, you remember band gap energy for metals or good conductors is minimum, and band gap energy for insulators or for non-conductors or for poor conductors, it is maximum. Okay, fine. Read number 4 now. See, they are asking about decreasing electrical conductivity of germanium, correct? Now, whenever you want to decrease the electrical conductivity, you should decrease the temperature. Among the 4 given options, for remaining 3 options, the electrical conductivity will increase, but they have asked about decrease in electrical conductivity, and that you can have by decreasing temperature. That's why I am writing here, by decreasing temperature. Okay. Read number 5 now. Come on. To detect the presence of light, we use photodiode, and that photodiode is always used in reverse bias condition. In reverse bias condition. So, to detect the light, what we should do? We should use this photodiode in reverse bias. Okay, fine. Come on, read number 6 now. Read it. They are given this sort of energy band diagram. You can see these extra energy levels, they have shown very close to this valence band, and this must be for P type semiconductor. If extra energy levels they are showing here very close to conduction band, then it will be for N type semiconductor. Right now they have shown these extra energy levels very close to this valence band, and that's why this must be for P type semiconductor. Okay. So, your answer is right now P type semiconductor. Got it? Fine. Read number 7 now. Read it. Out of the given diodes, out of the given constructions, which construction is always given forward bias? That is what they have asked. Among the given 4 options, this is the right answer, light emitting diode. LED requires always forward bias. Okay. Remaining 3 they have given, they require reverse bias, and here is the LED, which is the construction which requires always forward bias. Okay. Now, read number 8. Read it. Among the given devices, which device does not require any bias voltage? Among the given options, this is the solar cell which does not require any bias voltage. Okay. Remaining 3 require some bias voltage, whereas solar cell does not require any bias voltage. Okay. It converts, come on, light energy into electrical energy. Okay, it does not require any bias voltage. Fine. Read number 9 now. Read it? Come on. Electric field strength in the depletion layer should be equal to barrier potential divided by width of depletion layer. This barrier potential they are given 0.5 volt and width of depletion layer 5 into 10 raised to minus 7 meter. When this is in volt, this is in meter, naturally this will be obtained in volt upon meter. Answer is 10 raised to 6 volt upon meter. Okay, fine. Now read number 10. Read it? Among 4 given diodes, which diode has reverse bias? That is what we have to find out. In short, you know which diode will be in reverse bias. For that diode which is in reverse bias, remember the potential of anode should be low and potential of cathode should be high. So among the given 4 options, which diode has low voltage at anode and high voltage at cathode? That is what you have to find out. And it is none but diode D3 in this case. Come on, this is P-type semiconductor, this is N-type semiconductor, this is anode, this is cathode. What is the potential at anode? They have given 5 volt. Potential at cathode they have given 10 volt. So VA is 5 volt and VK is 10 volt. You can see 5 is less than 10, so VA is less than VK. I told you, for that diode for which the potential at anode is lower than potential at cathode, it must be having reverse bias. Okay, so this diode D3 lies right now in reverse bias condition. Okay, remaining 3 are in forward bias. We are asked to find out that diode which has reverse bias. It is none but diode D3. Okay, they may change the order, they may change the symbol. So just be very careful. Try to understand. The diode which has reverse bias must be having low potential at anode and high potential at cathode. Okay, fine. Now read number 11. Read it? This is a very good question. Very good. We are given 3 circuits. Circuit number 1, 2, 3. And both the diodes used in the circuit, they are identical. Fine. But they are not ideal diodes. They are practical diodes. And they are identical. So they have same resistance in forward bias condition. They have same resistance in reverse bias condition. Okay. Fine. Now tell me. In this first case, you can see both the diodes are forward biased because P with positive, N with negative. Okay? When both the diodes are forward biased, naturally current passing through both the diodes will be, because they are connected in series, it must be same, but that same current is passing in forward bias condition. So I am just putting symbol IF. Fine. Now for one diode, the resistance in forward bias condition I am taking as RF. What is the voltage drop or potential difference across any diode? It is current into resistance. Current is IF, resistance is RF. So IF into RF will give you voltage, not only across D1, across D2 also same will be the voltage, because current passing through both the diodes is same and both the diodes are identical. Their resistance in forward bias condition is also same. So I mean to say V1 equals to V2 equals to IF into RF. So in this first circuit, these two voltages are equal. Now the series connection is reverse. Now you can see both the diodes right now they are in reverse bias condition for circuit number 2, because come on, N with positive and P with negative. So both the diodes right now in reverse bias condition. In reverse bias condition for practical diode, some reverse current is flowing. Let it be shown by symbol IR. No doubt it is very small value of current, but it is flowing. And because it is series connection, same value of current will pass through both the diodes. And for one diode, if the resistance in reverse bias condition is RR, then what is voltage drop? It is current into resistance, so it is IR into RR, correct? And same will be the voltage across first diode also, same will be the voltage across second diode also. So I am writing V1 dash equals to V2 dash. Why I am putting dash? Because this voltage value is different than this, then I am putting different symbol. V1 dash equals to V2 dash, okay? And now in the third condition, they have given this sort of circuit. Come on, you can see first diode is reverse bias because N with positive, and second diode is forward bias because N with negative, okay? So first diode is reverse bias, it will have resistance RR, and second diode has forward bias, so it will have resistance RF, correct? And now because they are connected in series, same current will pass through both of them, let it be I. And now what is the voltage drop across first diode? It will be I into RR. Come on, I into RR, because it is in reverse bias condition. Let it be shown by symbol V1 double dash. And what about second diode? For second diode, because it is in forward bias condition, the resistance is RF, current is I only. So it is current into resistance will give you voltage drop, which is V2 double dash. No doubt I is same, but these two resistances are different. So these two voltage drops are also different. So V1 double dash is not equal to V2 double dash. V1 double dash is not equal to V2 double dash, okay? But you know what have they asked in the question? For which circuits the potential drops across each diode would be same? Then the final answer is, in circuit number 1 also these two voltages are equal, in circuit number 2 also these two voltages are equal. So our final answer will be, for circuits 1 and 2 the voltages are equal for both the diodes, correct? Fine. Now kindly read the statement of number 12. Read it? Fine. They are talking about half wave rectifier. For half wave rectifier, you know we use only one PN junction diode, and this is the load resistance. Moreover, they have given that maximum voltage between the two ends of secondary coil is Vm, and this diode is lying in a reverse bias condition. That is what they have given in the statement. For reverse bias condition, potential at P type semiconductor must be low, potential at N type semiconductor must be high. That's why I am putting here 0 and here I am putting Vm, okay? Potential at anode is low, potential at cathode is high. Now tell me, if you supply this much voltage, that is Vm minus 0, that is Vm, and then out of this supplied voltage you will have two parts. One part of the voltage will be obtained across this diode, let it be Vd, voltage across diode, and remaining part of the voltage will be obtained across RL, which will be current into resistance, correct? Fine. But now because this diode is lying in a reverse bias condition, there is no current. So I equals to 0, I equals to 0, put it here, correct? We should treat this diode as ideal diode, for which in reverse bias condition there is no current because of infinite resistance. Now when there is no current, I equals to 0, put it here. Put it here. When you put I equal to 0, you will get Vd equals to Vm. Vd equals to Vm, correct? So voltage across diode would be equal to Vm. That is maximum voltage in the secondary coil, okay? Now kindly read this statement of number 13. Read it. In case of LC oscillations, we used to find out frequency, and that frequency is found out from the formula f equals to 1 upon 2 pi into under root LC. But from that you can find out omega, and from that you can find out omega square. You will get this one. Omega square equals to 1 upon LC. What was the formula for omega? It was 1 upon under root LC. Take square, you will get omega square equals to 1 upon LC. Using this we can find out omega. Using omega value we can find out frequency value, correct? It is also called resonant frequency. What is it called? Resonant frequency. Fine. Then read number 14 now. Read it. For LC oscillations, you know the frequency formula f equals to 1 upon 2 pi into under root of L into C. Now in the second case, you know what have they done? They have made this capacitance value doubled. So naturally when you change this frequency will change. Let it change to f dash. But now new value of capacitance is double than earlier value. Earlier it was C, now I am placing 2C. Okay, instead of C you should write 2C because capacitance is made doubled. Fine. 1 upon under root 2 you can take separately. 1 upon under root 2 into 1 upon 2 pi into under root of L into C. Correct? Now tell me 1 upon root 2 as it is, and this is nothing but F. So this is nothing but F. So what have they asked? In the second case frequency will become how many times the initial frequency? It will become 1 upon root 2 times. 1 upon root 2 times. Correct? Fine. Read number 15 now. Read it. For any mode of connection of a transistor, remember, might be NPN, might be PNP, in every type of transistor, in every mode, remember always emitter junction is forward biased and collector junction is reverse biased. Come on, emitter junction is forward biased and collector junction is reverse biased. Correct? Read number 16 now. Read it. Come on, voltage gain AV equals to output voltage upon input voltage. Remember, voltage gain they have given 200, but we know voltage gain is always negative. So though they have given 200, we should take minus 200. Okay, transfer this VI here. So VO will be minus 200 into VI. This minus 200 as it is. What about input signal voltage? They have given in the statement as VI equals to 0.5 into cos of 313 into small t. Fine. Now minus as it is 200 into 0.5 will give you 100 into cos of 313 into small t as it is. Now this right hand side you can rewrite as 100 into cos of 313 t plus 180 degree, because 180 degree means pi radian and pi plus something. So you are entering into third quadrant. For third quadrant, cos function is negative, correct? And cos of pi plus theta, it is as good as minus cos theta, correct? Instead of theta right now it is 313 into t. So I mean to say this right hand side can be rewritten as this, okay? So this is nothing but the expression for output voltage. In this case, how much? 100 into cos of 313t plus 180 degree. Got it? Fine. Now read number 17. Read it? Out of total number of electrons which has entered from emitter into base, 90% of those electrons enter into collector, and that number constitutes collector current. So collector current is formed by 90% of this total number of electrons. Total number of electrons will form total current, that is emitter current. So in short, collector current is right now 90% of emitter current. And now tell me, this collector current they have given 10 milliampere. And how would you find out 90% of IE? Very simple. Come on, multiply IE by 90 and divide by 100. Multiply by 90, divide by 100. Find out IE. In this case, it comes out to be nearly equal to 11 milliampere. Okay. What is IB? Base current is IE minus IC, isn't it? IE we have obtained nearly 11 milliampere. IC they have given 10 milliampere. 11 minus 10, that is 1 milliampere. Okay. Kindly read this statement of number 18. Read it? Come on. For beta, what is the formula? What is the relation between alpha and beta? Remembered? We had obtained in the illustration. Beta equals to alpha upon 1 minus alpha. Alpha is current gain in common base mode. Beta is current gain in common emitter mode. Alpha is given to 0.99. Put the value of alpha 0.99. Simplify. You will get value of beta as 99. Fine. What about formula for modulus of voltage gain? That formula is beta into RL upon Ri. Beta into RL upon Ri. What is beta value right now? It is 99. Load resistance is given to 10 kilo ohm. Input resistance is 1 kilo ohm. Whenever it is a ratio of identical physical quantities, you just retain the same units. Okay. Both these values are given to in kilo ohm. Then leave them in kilo ohm only. No need to convert into ohm, because kilo ohm upon kilo ohm will get cancelled. Fine. Now this answer is 990. Okay. So magnitude of voltage gain right now it is 990. Read number 19 now. Read it? They have given this sort of logic gate, and we are asked to find out name of that logic gate. Let us find out. Here inputs are A and B. Because these two are NOT gates, they would perform NOT operation. So from A you will get here NOT A. From B you will get NOT B. But these two are now inputs for this OR gate, and you know OR gate will perform OR operation. That is, here you will get output capital Y equals to OR operation between these two, that is not A or not B. Come on, not A or not B. Correct? Remembered last time I taught you about De Morgan's theorem. De Morgan's theorem, one of the two theorems is this: not A or not B, it is as good as not A and B. Not A and B. Remove two small bar signs and big bar sign is to be placed, and instead of plus you are supposed to write dot. Okay. Now tell me, had it been only A and B, we could have called it AND gate, but because it is accompanied by bar sign, that is NOT operation, so you can say AND plus NOT. AND plus NOT is nothing but NAND gate. AND plus NOT is nothing but NAND gate. So I am writing answer NAND gate. Okay. Now at home you please try one more question. Leave these two NOT gates as it is only, but instead of OR gate you may place here AND gate. Okay. And then the whole logic gate will behave like NOR gate. NOR gate. Correct? Fine. If here it is OR gate, then it behaves like NAND gate, and here this OR gate, if you replace by AND gate, then the whole logic gate will behave like NOR gate. Okay, you may please try it at home. Now read number 20. Read it. See, you are given two input signals A and B. You are also given output signal. But if you minutely observe, then you will realize when both the inputs are 1, then only output is 1. When both the inputs are 1, then only output is 1. So it must be AND gate. That's what I have written here. When both the inputs are 1, then only output is 1. Correct? Hence the given gate must be AND gate. That is the speciality characteristic of AND gate. When both the inputs are 1, then only output is 1. Now read number 21. Read it? Fine. We are given two input signals. Come on. The combinations also they have given 1 1 1 0 0 1 0 0. Suppose I perform OR operation between these two inputs. OR operation. So A or B. OR operation means simple addition. Correct. 1 plus 1 you write 1 only. Don't write 2. 1 plus 1 that is 1 only. And here 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 that is 0. But now you perform NOT operation on this. So NOT operation means instead of 1 we should write 0. Instead of 0 we should write 1. And now tell me, whatever output they have given a capital Y, that output is also 0 0 0 1. And here also we are getting 0 0 0 1. Correct? So what does it mean? That this output and this output they are same, meaning thereby given gate must be behaving like that gate whose Boolean equation must be this. And what is this Boolean equation? Y equals to not A or B. Had it been only A or B, it is OR gate. But because it is accompanied by NOT operation, come on, OR plus NOT, that is NOR gate. So I am writing answer, final answer, NOR gate. Correct? Y equals to not A or B, it is nothing but OR plus NOT, which is NOR gate. Got it? Now begin the exercise numericals. Kindly read this statement of first numerical. Read it? Come on, free electron number density is given by formula Ne equals to Ne upon capital V. This is total number of free electrons, this is total volume. Fine. Transfer this. So you will get Ne equals to small ne into capital V. Small ne as it is, what is capital V? Volume of given crystal, and volume of given crystal, because it is in the form of rectangular solid, we can say volume is nothing but length into breadth into height. Length into breadth into height. Come on, this free electron number density they have given 6 into 10 is to 19 per meter cube. Because this value you are taking per meter cube, this volume I must take in meter cube. Now length is given to 1 centimeter, breadth is 1 centimeter, height is 2 centimeter. centimeter into centimeter into centimeter will give you centimeter cube, and whenever you require to convert volume value from centimeter cube to meter cube, you must multiply by 10 raised to minus 6. Centimeter cube to meter cube, remember, multiply 10 raised to minus 6. Okay, and now simplify. 6 2s are 12, 19 minus 6, that is 13. Okay, so in the given volume of given crystal, come on, there must be total number of free electrons. How much? 12 into 10 raised to 13. Got it? Fine. Now read number 2. Read it? Come on, remember this relation between the free charge carrier density for intrinsic semiconductor and majority and minority charge carrier densities for extrinsic semiconductor. Remember this relation? Ni square equals to Ne into Nh. Now right now they have added trivalent impurity. They have added trivalent impurity, so you are likely to get p-type semiconductor. And for p-type semiconductor, these holes are majority charge carriers, so this will become charge carrier density for majority charge carriers, and this will become minority charge carrier density, that is for free electrons. Fine. Now for intrinsic semiconductor, that is without impurity, the number of electron hole pair number density for electron hole pair, that they have given 1.5 into 10 to 16 per meter cube. Don't forget to make it a square. Okay, what is this Ni? It is number density for electron hole pair, which they are given as 1.5 into 10 to 16, and just make it squared. What is this Ne? Minority charge carrier density for p-type semiconductor, which we require to find out. What is this Nh? Majority charge carrier density for p-type semiconductor, that is for holes, and that they have given 4.5 into 10 to 22. And now simplify. Find out value of Ne, you will get it 5 into 10 to 9 per meter cube, that is unit will be meter raised to minus 3. Okay, fine. Kindly read the statement of number 3. Read it? Come on. Eg, band gap energy, by formula it is Sc upon lambda. What is H? Planck's constant, you are given in the statement, 6.62 into 10 to minus 34 joule into second. C is velocity of light in vacuum, everybody must remember, 3 into 10 to 8 meter per second, divided by wavelength of light, they have given 6000 angstrom. Convert it into meter, not centimeter, into meter. Angstrom to meter, you must multiply by 10 raised to minus 10. If you are placing all these values in SI unit, then this energy will be obtained in joule. But because we require this energy in electron volt, you must convert joule value into electron volt value. Come on, joule to electron volt, you must divide by 1.6 into 10 raised to minus 19, correct? And when you do that, the value of this energy in electron volt comes out to be 2.06875, that many electron volt. Okay? Kindly read the statement of number 4. Read it? Same formula once again we are using Eg equals to Sc upon lambda. Eg equals to Sc upon lambda. What about Planck's constant? As usual, 6.62 into 10 minus 34 joule into second. That value they are given in the statement. C is the velocity light in vacuum, 3 into 10 meter per second. What about wavelength? In this case, they have given 662 nanometer. Convert into meter, multiply 10 to minus 9. And if you are placing all these values in SI unit, unit of energy would be joule. But if you require this energy value in electron volt, joule value should be converted into electron volt by dividing with a factor 1.6 into 10 minus 19. Correct? And now if you simplify, answer is 1.875, that many electron volt. Okay. Remember the definition of band gap energy. The difference in energy between energy of lowest energy level in the conduction band and highest energy level in the valence band. That difference in energy between those two energy levels gives you energy gap. Okay, EG. Read now number 5. Read it? Come on. Electric field strength in the depletion layer, it is potential barrier, barrier potential divided by width of depletion layer. Come on. Find out VB from here, E into D. This electric field strength you are given in the statement 5 into 10 to 5 volt upon meter. What about width of depletion layer? 400 nanometer, converted into meter, multiply 10 to minus 9. Fine. Now this answer is 0.2, unit of barrier potential is volt, correct? Now when barrier potential is 0.2 volt, what does it mean? In order to have electron entering from N to P type semiconductor, you must push it, you must supply energy to that, and that energy, that forward bias should be either equal to this much or it should be greater than this. Okay, so by spending minimum energy, if you want to send electron from N type semiconductor to P type semiconductor, then minimum forward bias voltage required is this much, 0.2 volt. Okay, come on. And what is the amount of work done? Amount of work done is given by formula potential difference into charge. Potential difference is right now barrier potential VB, charge I am putting small e because we are talking about one electron. What is the magnitude of charge of one electron? It is small e. This barrier potential we have found out is 0.2 volt, and this magnitude of charge of one electron 1.6 into 10 minus 19 coulomb. But when you this value when you write in volt and this value in joule, in coulomb, then volt into coulomb will give you joule. I mean to say, when you place these two values in SI unit, you will get work done in joule. But if you require work done in electron volt, then joule to electron volt you should convert by dividing with a factor 1.6 into 10 minus 19. Correct? Simplify, these two values are equal, so they will get cancelled, giving you 0.2 that many electron volt. Correct? And as such also I have told you many times, as many volt potential difference, that many electron volt energy. Repeat, as many volt potential difference, that many electron volt energy or work. If potential difference is 0.2 volt, then corresponding work or energy would be 0.2 electron volt. Correct? Fine. Now read number 6. Read it? They have given this sort of circuit diagram in which these two diodes are ideal diodes. For ideal diode, remember, in forward bias condition the resistance would be 0, and in reverse bias condition resistance would be infinite. Fine. Now in the first case they have given potential at point A greater than potential at point B. When this potential is greater than this potential, this diode will be forward biased because P with positive, correct? So in short, diode D1 is forward bias, and in that case diode D2 is reverse bias. So I am writing here D1 is forward bias and D2 is reverse bias. Because this diode is in reverse bias condition, it will not allow any current to pass through it because it is ideal diode. Then because of high potential here, the current will flow this way, correct? And when current is flowing only through the first diode and not through the second diode, then current which is flowing through first diode will come across the resistance in this branch, correct? Then how much is the resistance in this branch? Because these two are connected in series, you must add their individual resistances. But for forward bias condition of this diode, its resistance is 0. 0 plus 50, that is 50. So resistance between points A and B, RAB, would be 50 ohm, correct? Fine. Now in the second case, they have reversed this condition. Now they have given VB greater than VA, VB greater than VA. So you can say VA less than VB, VA less than VB. Here potential is low, here potential is high. In that case, this D1 will be reverse bias and D2 will be forward bias. Come on, D1 is reverse bias and D2 is forward bias, correct? If D2 is forward bias, then current will pass through D2 only, correct? Current will not pass through this D1 because it is reverse bias. Come on. When current is passing through only D2, it will have resistance in this branch only. So it will be offered resistance in this branch only. Come on, what is the resistance in this branch? You can see it is a series connection. But because this diode is ideal diode, its resistance in forward bias condition is 0. 0 plus 50 will be 50. So again resistance between A and B, equivalent resistance will be 50 ohm. So I am writing RAB equals to 50 ohm, correct? Mind well, these two are ideal diodes, okay? Fine. Now read number 7. Read it? Come on, magnitude of voltage gain by formula mod of AV equals to beta into RL upon RI. Beta into RL upon RI. What is magnitude of voltage gain? 200. Beta we are looking for. RL load resistance is 10 kilo ohm. Input resistance is 1 kilo ohm. Come on, both this kilo ohm unit will be getting cancelled. Find out beta, and its another symbol is AI. It means to say current gain, it comes out to be 20. What about transconductance, GM? One small formula we had derived extra in theoretical part. Remembered, GM equals to beta upon Ri. When GM equals to beta upon Ri, this beta value we have found out is 20. What about input resistance? They have given 1 kilo ohm, convert it into ohm. Kilo ohm to ohm multiplied by 10 raised to 3. And now this answer is 0.02. Unit of transconductance is mho. You may write MHO or you may put this symbol. And SI unit of transconductance is Siemen. For Siemen, the symbol is capital S. Okay. Either you write Siemen or you write mho, one and same thing. Okay. Now read number 8. Read it? Come on. Because base current is 7% of total current, that is emitter current. Base current is right now 7% of emitter current. Remaining current must be collector current because total has to be 100%. So 100 minus 7, that is 93% of total current must be in the form of collector current. Now this collector current they have given 18.6 milliampere. How would you find out 93% of IE? You should multiply IE by 93 and you should divide by 100. Multiply by 93, divide by 100. Come on. Find out IE from here, you will get it 20 milliampere. And now in case of common base mode, what is the current gain? Alpha. What is this formula? IC upon IE. Alpha equals to IC upon IE. IC, they have given 18.6 milliampere. i.e. we have found out it is 20 milliampere. This upon this answer is 0.93, 0.93. Every type of gain is always unitless, correct? Now kindly read this statement of number 9. Read it. By formula, input resistance is change in base voltage divided by change in base current. This change in base voltage, it is as good as signal voltage, Vs. We had discussed in the theoretical part. In case of use of transistor as an amplifier, remember Vs equals to delta VBE. Vs equals to delta VBE. Fine. This delta IB as it is. This signal voltage, you are given 200 millivolt. Convert it into volt, multiply by 10 raised to minus 3. What about change in base current? They have given 200 microampere. Convert it into ampere, multiply by 10 raised to minus 6. Now this answer is 1000 ohm, or you may write 1000 ohm as 1 kilo ohm. Okay. First value you will get in ohm only, because this value we are putting in volt, this value we are putting in ampere. Volt upon ampere will give you ohm only, and later on if required you may convert, or otherwise not. Now voltage gain is output voltage divided by input voltage. This input voltage is as good as signal voltage, that is Vs. Now this output voltage you are given 2 volt, signal voltage they are given 200 millivolt, converted into volt, multiply 10 raised to minus 3. Simplify, answer is 10. So voltage gain value is right now 10. Actually it is magnitude. Okay. Read number 10 now. Read it. Come on, magnitude of power gain is equal to magnitude of voltage gain multiplied by current gain AI. Now magnitude of voltage gain by formula it is Gm into RL, and this AI can also be shown by symbol, another symbol, this beta. Instead of AI I am just putting beta. Beta and AI, they both indicate current gain in common emitter mode. This mode of AP as it is. What about transconductance? Its formula is change in collector current divided by change in base voltage. So come on, delta IC upon delta VBE, and into RL as it is, into beta as it is. What about value of power gain? They have given 4500. Change in collector current 10 milliampere, convert into ampere, multiply 10 raised to minus 3. This load resistance we want to find out. Beta current gain they have given 150. What about change in base voltage? They have given 100 millivolt, convert into volt, multiply 10 raised to minus 3. Simplify, find out value of RL. It comes out to be 300 ohm. So load resistance value in this case has come out to be 300 ohm. Now read number 11. Now just I am giving you one suggestion. Don't be afraid of the figures, the circuit diagrams which they given in number 11 and number 12. Don't be afraid of that. The sum is very simple. You simply remember the two equations which we had written in case of use of transistor as a switch. In case of use of a transistor as a switch, for input part we had written this equation, Vi equals to, remembered, IB into RB plus VBE. And for the output part we had written this equation, VCC equals to IC into RL plus VCE. Simply remember these two formula, the sum will be very easy for you. Come on, this input supply is, come on, 5 volt. This base current is we are looking for. What about resistance connected with base? They have given 100 kilo ohm, converted into ohm and multiplied 10 raised to 3. Kilo ohm to ohm multiplied 10 raised to plus 3. And come on, VBE, that is base voltage. And that base voltage they have given in the statement, it becomes 0. When we supply 5 volt in the input, this VBE becomes 0. That is what they have said. Now find out IB from here, you will get it 15 to 10 raised to minus 6, that many ampere. Or you may write 10 raised to minus 6 ampere as 1 microampere. So this is 50 microampere. Okay. What about the equation in the output part? Remember, VCC equals to IC into RL plus VCE. Come on, this collector supply voltage, they have given 5 volt. Collector current we want to find out. Load resistance is 1 kilo ohm, converted into ohm multiplied by 10 raised to plus 3. VCE becomes 0. The potential difference between collector and emitter becomes 0. That is what they have said in the statement. Now find out IC. It comes out to be 5 into 10 raised to minus 3 ampere. But 10 raised to minus 3 ampere is nothing but 1 milliampere. So this is as good as 5 milliampere. What about current gain in case of common emitter mode? It is IC upon IB. IC is 5 milliampere converted into ampere multiplied 10 raised to minus 3. IB is base current. That base current is 50 microampere converted into ampere multiplied 10 raised to minus 6. Simplify, answer is 100. Any sort of gain is always unitless. Okay. Now kindly read the statement of number 12. Read it. Just make use of the same two equations. Come on. VI equals to IB into RB plus VBE. Same equation. VI equals to IB into RB plus VBE. Correct? What about input supply voltage? You see in the diagram, input supply voltage, that is VBB, and output supply voltage, that is VCC. Both of them are 6 volt in the figure. Okay. So this input supply voltage is 6 volt. Fine. What about base current? Base current they have given 5 microampere converted into ampere multiplied 10 raised to minus 6. And what about RB? Base resistance they have given 1 mega ohm. Mega ohm you must convert into ohm multiplied 10 raised to plus 6. And VBE value we want to find out. Find out VBE, 10 raised to minus 6, 10 raised to plus 6 will cancel. 6 minus 5, that is 1 volt. Now apply equation for output part of the circuit. VCC equals to IC into RL plus VCE. Come on, this collector supply voltage is also 6 volt. What about collector current? They have given in the statement as 5 milliampere converted into ampere multiplied 10 raised to minus 3. What about load resistance? 1.1 kilo ohm converted into ohm multiplied 10 raised to plus 3. VCE we want to find out. That is potential difference between collector and emitter. Simplify, you will get the answer 0.5 volt. 10 raised to minus 3, 10 raised to plus 3 will cancel. 5 into 1.1, that is 5.5. Transfer it here. 6 minus 5.5, that is 0.5 volt. Got it? Now kindly read the statement of last example number 13. Read it. Formula for magnitude of power gain, it is beta square RL upon Ri. Had it been magnitude of voltage gain, then it is only beta into RL upon Ri. If it is magnitude of power gain, then it is not beta here, it is beta square. Take care. This magnitude of power gain, they have given 2000. What about current gain? They have given 100. It's a square, don't forget. And these two values you must write with the same unit. Come on, let it be both of them in kilo ohm. Come on, now I am writing this input resistance in ohm. Input resistance they have given 1 kilo ohm, but 1 kilo ohm when I transfer into ohm will become 1000 ohm. Now this RL I want to find out. because Ri value you are putting in ohm, naturally this load resistance will be obtained in ohm. It comes out to be 200 ohm. If they ask this load resistance in kilo ohm, you may divide by 1000, 200 upon 1000, that is 0.2 kilo ohm, correct? But they have not asked such, and they have asked only load resistance. That load resistance has come out to be 200 ohm, correct?